Lots of people. So just about everyone's here. How's everybody doing? Anybody have any questions of any homework stuff or anything like that? Just blurt it out if you do.
I just have questions about for the textbook because I'm taking your class next semester for 242?
Yes, ma'am.
Or we're using the same textbook we're using for this class, right? For the next.
That is correct.
And for that, because I'm thinking to get the homework code, there's two choices where you just get the code and it lasts for next semester too. But a separate code for it too, right? For next semester, it's not the same one for the homework.
Yeah, there's a cheaper version you can get where it's like only 18 weeks or something like that. Of course, our semesters last 16 weeks, so that would be a problem. You'd have to get a second one. So what you would probably want to shoot for is the 24-month deal or whatever the next step up is. Some students even do it differently because their concern is that they might actually fail, so they get a whole 2 years or whatever. But whatever one you want to do will be just fine. It's just a matter of paying more for it. So I would recommend you go in to the bookstore, get one that's long enough to last the 2 semesters, or log into the Mastering, MyLab and Mastering, create an account, and purchase the one that's long enough for 2 semesters. Because like I said, you will be using this both semesters.
Okay, so we don't have to buy the homework code again for next semester. That one.
Not supposed to, no. If you bought the 18-week one, that would be a problem. But I don't think they sold those at all at the bookstore.
Okay, thank you.
No problem. Anybody else have any questions? We're going to find instruction on how to register and class. Okay, so you shouldn't be using the class code at all. I have my MyLab and Mastering actually integrated with my learning management system. That's what they call Canvas, Blackboard, Moodle, all those things. They're called LMSs or learning management systems. My course is actually integrated with that, so you don't need a class code. All you have to do is go to Canvas, click on the MyLab and Mastering link, and it'll ask you to register. At that point, you put in your access code that you purchased, or like I said, I think they give you a 1 or 2 week grace period. So if you don't have it yet, you can use it for 1 or 2 weeks, and then boom, it blocks everything until you actually purchase the setup. And that way, you can actually choose the actual cheapest way to purchase the textbook at all is just buying an e-text with access to the MyLab and Mastering and buying it right through there. It's cheaper. But again, if you need to use financial aid or stuff like that, you have to buy it through the bookstore, and that's a little bit more expensive. Anybody else have any questions? Like I said, you can chat or you can just verbally speak out. I'm watching the chats as well as everything else. So let me put it back on everyone, just in case I send y'all a chat and everybody screws up. Little ways through the class or right before the end, I'll get you guys to chat again with your first and last name. Remember, all these videos go on my YouTube channel, so if you don't want your name up there, you want to change it to just your first name, that would be fine. So make sure you let me know about that. Can't believe how much of a lag there is between my words and my lips on the TV, or excuse me, on the monitor. Oh, by the way, see my cool shirt? Woohoo! Plus, you saw this manly figure. Could you see my abs? They were abs, right? They're hidden under a deep layer of adipose tissue. All right, so it looks like we don't have any more questions regarding syllabus stuff like that. I did update the syllabus yesterday. I sent you all an email. The homeworks for the first 2 chapters are up. As far as the lab goes today, no one objected to starting early. So I think that means we can start immediately after class, which means we'll start right after. Like I said, I'll probably give you a 5-10 minute break, and then we'll jump right in. You actually log off because I'll go to lecture course, to the lab course, to create another Zoom meeting, and then you log back in with that one. Actually, I just remembered I did not send y'all an invitation, so I'll have to do that in that little break. So y'all will get an invitation to the Zoom meeting in the little break that we have. The good news is I'm working in about a chapter a week. I did get a final say on what chapters I want to use. I don't know that I'm going to go back and update the syllabus. I might just put the list of chapters we're going to cover, but it's a lot more reasonable than I thought. I was afraid we were jumping around, skipping a lot of stuff, but we don't skip a lot of stuff. We just basically go through mechanics and all that good stuff and then jump to relativity. So we'll get there. So I answered the question regarding the lab, and I'm not doing, like I said, I'm not doing the hour break. Now's the time to let me know if anybody can't do it. I asked everybody to email me already, so I should have known, but no one did, so I'm assuming that means everybody's okay. If you really need that break, y'all need to let me know now, and we'll just set it up for 1 o'clock from now on. All right, well, let's get started. I'm going to start off with sharing my screen. And I think I'll do this one right here. Okay. Also, this screen, I can go to our course. I want to show you where everything is. So those of you who are wondering about how to register and all that stuff, you don't need a course code. You just come right to Canvas and you click on this. When you click on this, you'll see this. And then you click on that. I think with y'all, if y'all haven't started it yet, it'll say let's get started or something like that. So is that what y'all remember it saying? Get started or whatever. You click on that, and that's where you make an account if you don't already have it. When you get in there, there's an area called assignments. And I think you can even sometimes reach them through this way, student links. Yeah, so you can go straight to assignments with this link if you want. I don't have it both in calendar form as well as you can choose the list form. But in calendar form, you know what's immediately due and what's due and when. So that might be helpful. You can also do, of course, once you get in here, you can click on e-text. This will be what's happens when if you just click in get started where it says get started once you've already registered. If you click in My Lab and Mastering, this is where I think you'll end up. And you click on here for your e-text, you won't see these things that have the little locks by them, but you view the e-text, and that's where I'm going now. So last time this was not what I did. This was the previous class. I should put a bookmark on that. Okay, so I'm going to go to chapter 1, which is volume 1. And you'll probably notice, and I'll pull that back in a second, you'll probably notice I put some more videos up as well. I'm waiting for this to load. While I'm waiting for this to load, I'm going to go back to our Canvas page. So this is all the generic stuff that everybody has, blah, blah, blah. I did include a video about our syllabus. You might want to check that out. I think I did a good job with that one. This is the updated form of our syllabus, so this is the relevant one. And if I put any more, it's always the one with the latest date. Notice this is 8/25/2020. So that's important. The thing that I was trying to show you, though, is since last time where I already had measurement and uncertainty up, I put in Sig Figs and when they go wrong, which is a video that tells you how to use Sig Figs. And actually, some classes, some instructors are very strict. They use rules about not only are your Sig Fig rules have to be used, but in fact, they're sometimes erroneous and you're supposed to catch those. I'm not that particular about it, so I'm not going to make you catch those little errors where the Sig Fig rules go wrong, but I do expect you to be able to use your Sig Fig rules. Also, some teachers are quite pedantic about how to round off numbers. Specifically, they're concerned with how that 5 is sort of unfairly a critical number. It's in the middle, so why should you do all of them rounding up? So they devised a way for you to round half of them down and half of them up. And that's all in this video. I apologize in advance. I did it this morning. Wanted to do it yesterday. As soon as I started, my dog started barking. So you'll hear bah, 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 my little chihuahua barking all over the place. I apologize for that. I'm going to remake it. When I do, I'll post that newer version without the barking dog, Hercules. So anyways, and here's a document that I use in that. So you actually have a PDF version. You can follow along with it if you want. Finally, I did another video on scientific notation and dimensional analysis. And you'll see that these are basically all the parts of chapter 1 that are relevant. I'm going to move this to the very top because that was our first lecture, and today's will be called lecture 0826-2020. Some reason it's not telling me a password with these guys anymore, so I'm not really sure why, but anyways, it did with this one. That's weird. And this might I don't know what the difference between this video is and that video. I don't remember posting that, but anyways, y'all can check all that out. So everybody sees where all our stuff is and how to get to MyLab and mastering. So here's the e-text, and the big thing they're trying to pound here is that idea of a basically a scientific method. And remember, I showed you it last time in the last video as basically a cyclic process where you observe some phenomenon, or even you, like Einstein used to do, you just you just think of some scenario in your head and try to reason out what could cause that, and from that you make a hypothesis. With that hypothesis, you then use the hypothesis to make a prediction, and then that prediction must be tested by another observation. And if that prediction is not falsifiable, then it's not a scientific prediction, and it's not really, doesn't really have a place in science. If it is falsifiable, then you either get a yeah, you're right, or no, you're wrong scenario. And if you're wrong, you either have to repair it or throw the whole theory away, or throw the whole, hypothesis away. If it's really a robust, big idea, you probably don't just throw it away. You tweak it a little bit, and then make another prediction, make another observation, make another prediction, make another observation, and keep on doing that forever until basically you're really, really confident in this hypothesis. Once you've reached, hundreds of thousands or even millions of trials with no errors, no erroneous hypotheses, no erroneous predictions, then it becomes a full-blown theory. So that's the nature of science, and that we've already sort of discussed. It mentions models, theories, and laws. I've sort of expressed that to you. Once it becomes a theory, law can mean a couple different things, and I try not to hit that as a big question, just because there's so many different ways of thinking about laws. But laws can be something that's just observed in nature. Pressure and volume are inversely related. Sorry, I keep yawning. Pressure and volume are inversely related is one of the ideal gas laws. That's the one for the scuba divers, Boyle's law. So that's a very important one, and that's just an observational law. So they named it a law because it appeared to be true no matter what, and it wasn't tied to any particular theory. Ultimately, we made use of it to create the ideal gas laws. Measurement and uncertainty. The big thing with that is every time you make a measurement, as I mentioned before, you're going to get a certain amount of uncertainty in your measurement. Even if you're reading a digital scale, you have to understand that that last digit on the far right end is doubtful by at least 1 in that last digit. So plus or minus whatever that last digit is. If it's a hundredths place, you say plus or minus 0.01. If it's a tenths place, like on a typical car odometer, it's plus or minus 0.1. And that's the bare minimum. And like I said, as I showed you last time when measuring a binder clip versus a old school iPad charger, the old school iPad charger had rounded edges, so I had to estimate roughly where the thing was lining up with the ruler, in which case that introduces more uncertainty. So maybe that's not 0.01, but shoot, darn it, but rather 0.02 or maybe even 0.03. Sorry about that.
Is
yes.
Is uncertainty subjective in that kind of sense? There's no right or wrong answer.
Yeah, there are times when it's subjective. So, for instance, when you're making a measurement with a vernier caliper, you can get a very precise, ideally a three decimal place measurement, and the uncertainty in that last digit, you might estimate it to be different from someone else because your thing that you were measuring was bumpy or, cattywampus as opposed to nice and square. But someone else might have a different object that they're measuring, in which case they would say it's 1 in that last digit. So it is somewhat subjective. But what you're supposed to do as a scientist when you're making such a measurement is put down your best estimate and realize that there's a plus side and a minus side to both sides. If you make the estimate too small, say you say it's 0.01, that means you've got less range for error in the actual experimental results, because what you'll do is you'll make predictions based on those measurements, and the error, if it's really, really small, the error allowed in the prediction becomes really, really small. So you have to be really, really correct to get in that spot. Whereas if you realize there is more uncertainty to the number that you're measuring, then that uncertainty is bigger, and the uncertainty in the prediction is bigger. So you end up getting a little bit better chance of hitting the mark if you want your hypothesis to be correct. At the end of the day, you shouldn't be wanting your hypothesis to be correct or incorrect. You're just wanting the hypothesis to be answered. So that's one of the things we really try to stress, is letting you know that making an errant hypothesis is not a bad thing. In fact, the vast majority of huge discoveries come from someone making a incorrect hypothesis and being corrected, and then there's big discovery. So with that, so really what matters is this thing called fractional uncertainty, and I've talked about, you'll see in those videos, I've talked quite a bit about how significant digit rules work and stuff like that. And I'll go over that again, but at the end of the day, what really matters, if you take two numbers and say you're multiplying them, or maybe you're adding them to get a new answer, you should always think a little bit about the fractional uncertainty of the numbers. And what I mean by fractional uncertainty, if you had a number like 8.8, if they didn't take the time to express it as 8.8 plus or minus 0.1, then you would have to assume, because the decimal, it only goes to one decimal place, you would have to assume the uncertainty is 0.1. This time they were actually kind, and they gave you 8.8 plus or minus 0.1, so you know that's the actual uncertainty. If the person had measured this 8.8 centimeters, but it was like on some rounded edge thing, then it was their job to make this 0.2 or 0.3 or 0.4. Otherwise, if you just recorded as 8.8, everybody's going to assume it's 0.1 uncertainty. What that means as an uncertainty of 0.1 is that there's a probably 63% chance that the number could be anywhere between 8.7 and 8.9. Now, what is the fractional uncertainty? Well, the fractional uncertainty is when you take the uncertainty, 0.1 in this case, and divide it by the value, 8.8 in this case, and then of course you convert it to a percent. What you'll see is this is roughly 1%. Well, if you took this number and then let's say you had to take the sign of it, maybe it's in degrees instead of centimeters, and you took the sign and then you, according to the significant digit rules, this has 2 sig figs, so you would round the result from sign of 8.8 to 2 sig figs, then you'd calculate that fractional uncertainty. If that fractional uncertainty was on the order of 1%, let's say from 0.5% up to say 5%, then that would be a good round off point. If you, on the other hand, calculated that the error was like was like 7%, which is really close to 10%, then you maybe need to carry an extra digit. Okay, so that's the real truest of the rules. And like I said, if you take an actual more advanced science curriculum, you're going to go through courses where they teach you about propagation of error and proper analysis of numbers and statistics and stuff like that. But for right now, we're going to use the significant digit rules, and I'll ask that you watch for errors in Sig Fig rules, but I don't expect you to always catch them. So let me show you a little example. I'm going to turn it to my document cam. And let's say you want to multiply number 8.8 centimeters. Maybe you measured this little rectangular block and you're trying to calculate its volume. You measured one to be 8.8 centimeters, say the length. And remember, there's no definitive what's length, what's width, what's height. It's always what you decide it to be. And you measured the width to be 9.623 centimeters, and you measured the height to be 1.0 centimeters. Okay, notice that 1.0, if you put 1 in your calculator and then you put minus 1.0, your calculator is going to give you 0, like those two numbers are the same. But in the scientific world, in the laboratory world, those numbers are very different. You know, if I go to someone, say a machinist, and have them make me a block that's 8.8 by 9.9623 by 1.0, if I want this thickness to only be 1 without the 0.0 on it, then I can get a very cheap job done. In other words, the machinist isn't going to charge me much. But if I tell him I want it 1.0 centimeters, and he knows it's got to be plus or minus 0.1, so it's going to cost me a little bit more. In fact, this 9.623 centimeters is going to cost a lot more money. In fact, he's going to have to do some serious work to make sure his error is only 1 in this third decimal place. So that's some of the difference. But experimentally, I think you can see the difference. Well, let's say the volume is length times width times height. When you go to multiply these numbers, you get a whole big mess. You get 8.8 times 9.623 times 1.0. You get 84.6824. So that's the result of doing that multiplication, but is that really right? Well, if you look at multiplying 1.0 times 9.623, this is part of the multiplication, right? What we know is that this digit right here is doubtful, and this digit right here is doubtful. And you can't have any more than one doubtful digit. So when I carry out this multiplication, I get 0 times this, it's just 0, 0, 0. All of those are, of course, doubtful digits. 0, 0, 0, 0. And they're doubtful because I'm multiplying it by 0, which is doubtful. Then I got to put my placeholder, and then I do 1. 1 times 3 is 3, 2, 6, 9. Of course, when I did the 1 times the 3, I got a doubtful digit, so that guy was doubtful. Now I have to add these numbers and then put the decimal in the right place. So it'd be 0, 3, 2, 6, 9. And I see that this digit is doubtful, this digit is doubtful, this digit is doubtful, this digit is doubtful. I'm really only allowed to have one doubtful digit, so that tells me I have to round to just 2 digits. And of course, once I include the decimal, it's 1, 2, 3, 4, 1, 2, 3, 4. So my decimal point is going to be right there. So that would require me to say 9.6 is the answer. In this case, it's in square centimeters because I just did the bottom 2. So what the rule is, it turns out, is that the significant digits involved tells you the number of significant digits the final answer should have. So the factor in this case, since it's multiplication, they're called factors. The factor in this case with the smallest number of sig figs is this one, and they each have 2. So having 2 sig figs means you have to round this off at 2 sig figs. So this is going to be 85 cubic centimeters. Okay. Now we should check 0.1 divided by 8.8. Luckily, your book already did that one for us. But it didn't give me enough digits, so it's 0.011. So that's about 1%. The 0.1 over 1.0 is obviously 0.1. That's on the order of 10%. And of course, the 0.001 over 9.623, that's a really low number, 0.001 divided by 9.623. That's in fact 0.01%. So what we see is our error should be no smaller than roughly 10%. If I take the error in the 85, I do 1 over 85. And I get about 1%. So that error is about 1%. One of these numbers did have an error as high as 10%. So that's kind of problematic. You might even argue that this should have been 1 sig fig in this case. So that's sort of the danger here. You don't want your error in the final result to be much smaller or much bigger than the fractional uncertainties you had in the original numbers. Since this fractional uncertainty of the final answer was 1%, and two of these were 1%, one was 1%, one was 1/100%, and one was 10%, I would probably leave this just because this one's so small, that one's right on the mark, and then this one does less than compensate for that one. So I would basically say that would be okay. So that's our first rule. When we multiply, and it turns out the same case when you divide, when you multiply or divide, you find the factors in the case of multiplication, or you find the divisor or the dividend, or excuse me, the minuend, not minuend, the divisor or the factor, and that has the least number of sig figs, and that dictates how many sig figs your final answer will be. You'll see that in the actual sheet that I posted on Canvas. When you add, it was a different story. Remember, when you add, let's say we add 1.0 centimeters to 9.623 centimeters. So now we're trying to do, say, something like the perimeter, if that really matters. 8.8 centimeters. Obviously, it's not really a perimeter because it's 3 different directions. So anyways, all of these are centimeters, so I can't actually add them. And really what I'm doing is I'm pretending I'm adding zeros there, but those zeros are completely uncertain. So what we see is a 3 happens here, a 2 happens here, an 8 and a 6 gives you 14 happening here. Carry the 1, 1 plus 8 is 9, 9 plus 9 is 18, 19. So it'd be 19, and then of course my decimal place is there, but I see that all 3 of these numbers were doubtful because 2 and 3, only the 3 was doubtful, but there was nothing back here, so those were automatically doubtful. So this number is going to have to be rounded to 19.4 centimeters, and that's understood to have a doubtfulness of plus or minus 0.1. Again, you could look at the percent uncertainty or the fractional uncertainty. So if I do 0.1 divided by 19.4, I get about 0.5%. We know the fractional uncertainties of these guys ran from 0.001 to 10 and so on and so forth. I'm going to go with that, but this is one of those cases where an instructor might actually ping you and say, hey, that's a little bit too much uncertainty. But when you start to do that, there's definitely other ways to do it. It turns out, just quickly, since this is a calculus-based physics class, and I used to actually teach this in my calculus-based physics class, when you have an f that is a function of x, y, and z, say, or in this case, it could be L, W, and H, then basically you can talk about the uncertainty in f is equal to the derivative of f with respect to x, never mind those symbols not being a regular d, I'll explain that in a second, times the uncertainty in x. And this is the symbol you use for that little plus or minus that I keep drawing. The sigma is what you use for that little plus or minus. That'll be squared plus the derivative of f with respect to y. That'll also be squared times sigma y squared plus the partial of f with respect to z squared times sigma z squared, and take the square root. That's the actual way you do this. So bickering about whether this is about right or not close enough, or whether this is about right or not close enough, is kind of goofy because really you should be doing it this way. So what do these little weird symbols instead of the D's mean? They mean you pretend all the other variables are constants. So if my function is v equals L times W times H, and I'm taking the derivative with respect to L, then W is like a 4 and H is like a 2. So if I had 4 times 2 would be 8. 8L, what's the derivative of 8L? Just 8. So that's what I'd put here is WH squared, and so on and so forth. Put all that in, plus the plus 0.1, plus the 0.001, plus the, you know, whatever that is, but keep on doing that, and that would give you what the uncertainty is, and then you'd know immediately where to round the final answer, either be it in this problem or this problem. Okay, so that is really what the error propagation formula would tell us to do. So that being said, I think we now have a pretty good idea of what the significant digits come about, how they come about, and why we use them, because they're a really quick and dirty way of rounding numbers off properly, or pretty close to properly, so that we don't overestimate what we know or underestimate what we know. So back to sharing my screen. So that's the whole deal on measurement and uncertainty. And for some reason, it won't let me change my page. There's the button. Okay, gotcha. The buttons disappear sometimes. So the other thing that we often do is, in addition to using Sig Figs for data, we also use scientific notation, because the Sig Fig rule that I use is, I wrote it before, but the leftmost non-zero digit is the most significant digit, what I call the MSD. If there's a decimal present, the rightmost digit is the least significant digit, or the LSD. But if there isn't a significant digit, I mean a decimal present, then the rightmost non-zero digit is the least significant digit, or LSD. So let me look at some examples to tell you what I'm talking about. Let's say 0.000004910. So according to our rule, the leftmost non-zero digit is the most significant. So that's our MSD. And then there is a decimal present. So when there's a decimal present, the rightmost digit, period, is the LSD. So there's your LSD. And then the final rule is the MSD, the LSD, and everything in between are significant digits. So this, in fact, has 4 sig, and here I'm going to change up the words, 4 sig figs. So a lot of people use the word sig figs instead of significant digits, and the reason why is so 0.00004910. Again, the leftmost non-zero digit is the most significant, so I put the MSD right there. If there's a decimal present, that's the case here, the rightmost digit, period, it doesn't have to be non-zero, the rightmost digit is the least significant, so I put the LSD there. And then the final rule is the MSD, the LSD, and everything in between are significant digits. So 1, 2, 3, 4 sig figs. And sig figs just rolls off your tongue easier than sig digs. So that's why I'm going with that. Here's another example, and this is the one that stumps people in their textbooks. If someone says 500, then clearly the leftmost non-zero digit is the MSD. And there's no decimal present. I didn't physically write a decimal, so the rightmost non-zero digit is the LSD, because there's no decimal present. So the 5 is the LSD as well. So this one, in fact, only has 1 sig fig. But all day long, if your textbook gives you 500, you're supposed to pretend like that has 2 or 3 sig figs. So be careful with that. I'm not so stringent. If I want to be stringent on sig figs, I'm going to use scientific notation, so that this number will in fact be 5.00 times 10 to the 2. Okay, that solves that, oh crap, it doesn't have a decimal deal. Okay, So I think with that and the other videos I've shown you, you've had plenty of examples of how to use sig figs and scientific notation. The big deal with scientific notation is like this. Let's say we have a number 0.000014, and I want to put that in scientific notation. The rule is that there's a mantissa. There's a number part, if you will, to the scientific notation. And that number has to be greater than or equal to 1, but less than 10. Notice it's just less than 10, okay? And then this number will be equal to the mantissa. I like that word. Not a lot of people remember that's the proper word, but I just like it because it sort of makes me think of a sea creature, times 10 to some power, okay? That's the rule for for scientific notation. The mantissa has to be between 1, but it could be as small as 1, and 10. And then you have that times 10 to the something. So what I know is when I multiply, 41 times 10, I get 410. Whoa, 410, right? The decimal, which was assumed to be here, all of a sudden went over one place. That's what happens when you multiply by 10. If I multiply by 100, it moves 2 places. If I multiply by 1,000, it moves 3 places. Similarly, if you divide, it goes the other way. So if I want to make a mantissa out of this number, I need to move the decimal not here, because that's still less than 1. Not here, that's still less than 1. Not here, that's still less than 1. Not here, I'm still less than 1. Here, I'm greater than 1, but less than 10, so that works. And in fact, that took 1, 2, 3, 4, 5 moves to the right. So really what I got to do is I got to multiply that mantissa by 1 followed by 5 zeros, which can also be written 1 followed by 5 zeros is the same as 10 to the 5th, okay? So I had to multiply this number times 10 to the 5th to make it into the mantissa. But by doing that, I've changed the number. I don't want to change the number. I need the number as is. So what I also have to do is divide it by 10 to the 5th. So I take 0.000014 and I multiply it by 10 to the 5th, and then I divide it by 10 to the 5th. Well, that multiplying by 10 to the 5th makes it 1.4. Notice all those digits were non-significant, so they're not there. But now I got to divide it by 10 to the 5th, which if you remember your rules from division, A divided by B is defined to be A times 1 over B. So I can say this is 1.4 times 1 over 10 to the 5th, which is the same thing as 1.4 times 10 to the negative 5th. Because when you flip over a number, you've changed its exponent from 1 to negative 1, or in this case, from 5 to negative 5. So that's how you do scientific notation. That's how you convert, say, a very small number to scientific notation from standard notation. If you had a big number, let's say we had 3,000, let's do 3 million. Okay. Well, I still need that mantissa to be between 1 and 10. So I got to move the decimal 1, 2, 3, 4, 5, 6 places. So that's the same as dividing by a million or dividing by 10 to the 6. So I'm going to do 3 million divided by 10 to the 6, but I've already changed the value and that doesn't help. So to cancel that effect out, I have to multiply by 10 to the 6. So dividing by 10 to the 6 gave me the 3.0, and technically I should have just wrote this as 3 with no 0.0 at all, because there's no reason to believe any of these zeros are significant, but I'll just leave it there. Actually, no, I'll scratch it out to be pedantic, okay? So now I've taken care of this part, so I must call this 3 times 10 to the 6. And that's how you convert a big number from standard notation to scientific notation. If you have a number that's not that big, let's say, that's in standard in scientific notation, but it might not be that big, then how do we go the other way? well, let's say we had the number, let's say 3.69 times 10 to the 5th meters per second, say. Okay. What this is saying is, hey, I'm going to multiply that by 10 to the 5th power, and we know that means move the decimal 5 places to the right. So I'm going to say 3.69 is going to become 1, 2, 3, 4, 5. So it's 369,000 meters per second. See, I just read it off and do the math. That's all you have to do the actual converting scientific notation to standard notation. Here's another example. 1.602 times 10 to the negative 19th coulomb. So this is a really small number. In fact, it's the magnitude of the charge of the electron. So what this one's doing is saying, hey, there's a negative sign there. So that means I'm dividing by this without the negative sign. So I'm dividing by 10 to the 19th, which means I should move this decimal 19 places to the left. So I write 1602, and then I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There you go. So it actually has 18 zeros followed by 1602. And that comes out coulombs. Okay. So that is a important thing that you're going to have to do this whole semester. The only other thing you're going to have to do really is from this chapter is we've got to understand our base units. Remember, you have a base unit in the SI. And that would normally be the thing without a prefix, okay? In this case, though, when we talk about mass, it's a weird case where the base unit is actually the kilogram, but other than that, everything's pretty straightforward. So we have a base unit, and then if we make it really, really big, say we have something that's really big compared to the base unit, then we do something like this: T dash dash G dash dash M dash dash K. Okay. H and DA. Okay, so there's your prefixes in the SI system. That's tera, giga, mega, kilo, hecto, deca. And then if we go the other way, it's deci, centi, milli, dot, dot, micro, dot, dot, nano, dot, dot, pico, dot, dot, femto. Okay. So those are your prefixes. I think you can tell by the dots and everything. This means times 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 6, 10 to the 9, giga or giga as they pronounce it in Back to the Future, and 10 to the 12th. And the inside cover of your book has even more, so it goes further than this. This would be a unit like the meter or the kilogram or the liter or something like that. This is 10 to the negative 1, so that's a tenth of a meter. 10 to the negative 2, that's a centimeter, which is a hundredth of a meter. And then 10 to the negative 3, 10 to the negative 6 is a micrometer. That's the Greek symbol mu. It's a micrometer or a micron. Then 10 to the negative 9, 10 to the negative 12. Oh, did I skip one? 10 to the negative 3, 6, 9, 11, 12, 10 to the negative 15. Okay, so those are the bases we're going to use, or excuse me, the prefixes we're going to use. And that sometimes can let you even avoid stuff like scientific notation because you can just put a prefix on it to make the number small or big as you need it. So with that, we need to learn how to convert units. So let's take something simple. Let's say, for instance, there is something that my mother used to say, your mouth's running a mile a minute. So let's convert a mile a minute to, let's say, miles per hour. So 1 mile per minute. Okay. I would like to convert that to, say, miles per hour, and then I'll do something like convert it to centimeters per second or something, just for the heck of it, okay? So first off, we could start by converting it to miles per second, okay? Or we could just go straight to miles per hour. So the way we do it with unit conversions is, in most cases, units convert via just multiplication. There are some cases where units convert via formula. So we're not dealing with that right now. We're not dealing with converting Celsius to Fahrenheit and Celsius to Kelvin and all that stuff. We're actually dealing with multiplicative units. So in this case, I'm going to convert to miles per hour. And what I do to make a conversion by multiplication is you can only multiply by 1. Because if I multiply this number by anything other than 1, I change its value. Just like when I was doing scientific notation, if I multiplied that by 10 to the 6th, then I also have to divide it by 10 to the 6th, so it's not changing the value. But the cool thing is there's a lot of ways to write 1. You can write 1 as 1 over 1. You can write it as 2 over 2. You can write it as 3.14159 over 3.14159. Let's take it a little bit more abstractly. We can write it as 1 foot over 12 inches, right? The key is that the numerator is equal to the denominator. We could also write it as 1 hour equals 60 minutes. Or we can write it as 60 minutes equals 1 hour. Do you see either of these two being helpful in the problem above if I'm trying to convert that to miles per hour?
The last one.
The last one. Yeah, see the minutes being on top with the minutes down here, that works out really nice. So I say 60 minutes equals 1 hour. And what I see is my minutes units cancel out, and I'm left with miles per hour. So when my mother said I was talking a mile a minute, she really meant I was speaking at 60 miles per hour, or what we call 60 mph. So that's kind of neat, right? You can even be more complicated than that. Let's take 60 miles per hour. And let's convert that to meters per second, because that's the figure we're going to use way more often in physics. So I don't remember, well, I remember a lot of things, but I don't remember like every little conversion. Like I don't know how many miles there are in or how many meters there are in a mile and stuff like that. But watch what I do remember. I do remember that 1 mile is equal to 5,280 feet, right? So I can make a 1 out of that. I can make it 1 mile over 5,280 feet, or I can make it 5,280 feet over 1 mile. Which one of those do you think would be helpful to us in this case? I'm trying to get ultimately to meters per second. So which one's going to let me get rid of that mile? The mile on top or the mile on bottom?
The mile on the bottom.
Exactly. So I put 1 mile on the bottom. Now I know what my fraction is, 5,280 feet. Okay. Now what I've gotten is rid of the miles, and I'm in feet per hour. That's still not where I want to be, but I do know that there's 12 inches in 1 foot. So I can get to inches, which will help me because I absolutely know the conversion factor between inches and centimeters. In fact, it's exact. There's no uncertainty in it. It's exactly 2.54 centimeters is exactly 1 inch. That's what the inch has been defined in terms of. So by doing it this way, I actually am not introducing any error whatsoever. I'm using all infinite decimal places. So first off, let's go ahead and convert from feet to inches. Where should the feet be if I want to convert from feet to inches in this problem? Top or bottom?
Wait, you're going from feet to inches, so feet would go on the bottom, inches on top?
Yes, you want the feet in the bottom so it'll cancel out. And you want the 12 inches on top. Okay, so now I'm going to use a different symbol for this canceling out of feet. I should have just marked that on the feet, but I did the whole number like a crackhead. Never mind that. Okay, now I can get from inches to centimeters, but where am I going to have to put the centimeters, on the top or the bottom? Notice I'm asking a different question than I normally ask.
Put on top.
Top.
Exactly. The centimeters goes on the top, so I'll write 2.54 centimeters is equal to 1 inch. And now I'll write a different symbol for canceling these out so I can follow it later. So notice I did top left, top left, top left to bottom right, top left to bottom right. Then I did top right to bottom left, top left, right to bottom left, and then a full X. Just a way you can keep track, so if you ever make a mistake, you can look back and see where your error was. So at this point, I'm now at centimeters per hour. So that's pretty close. What I want is meters per second. Okay. Well, I happen to know, or you happen to know, how many centimeters are in a meter?
10
Anyone?
to negative 3 is the centimeter. No, 10 to the negative 2.
There you go. Good job. Just like cents in a dollar, that's where it came from. So in fact, 1 meter is equal to 100 centimeters. So am I going to put the centimeters on the bottom or on the top?
You put the centimeters on the bottom.
Exactly. 100 centimeters on the bottom and 1 meter on top. So now I'm at meters per hour. So now I'm going to do yet another symbol, a squiggly tilde looking thing, a slanted tilde. So now I'm to meters per hour. Does anybody know how many seconds there are in an hour? Or do you want to go first to minutes and then to seconds?
3,600, right?
Yeah, there you go, 3,600. We could take 2 steps if we wanted, though, but I'm going to go ahead and skip that step and just say 1 hour is equal to 60 times 60, or 3,600 seconds. Okay, so where do we want the seconds in this case? Notice that's a slightly different question again. Do I want the seconds on the bottom or in the top?
You would have
The bottom.
The bottom.
Right, because this is a weird thing. I'm actually converting a denominator. So to convert a denominator, I have to cancel out on top. So that means I need my hour on top and my seconds, which is what I want, on the bottom. So that finally gives me another squiggly this way. And I'm finally left with just meters per second. And how do I do such horrible, horrible math? Someone's actually typed up all this stuff for me. In fact, what I do when I get to this point is I just multiply all the numerators, 60 times 5,280 times 12 times 2.54 times 1, get that answer. And then I divide by this denominator. Actually, I'm doing the ones too, but you don't have to, obviously. I divide that answer by this denominator, hit equals, and then I divide that answer by 3,600 and hit equals, and I am golden. So I will do that real quick. I used to know this off the top of my head. I really should now. So 60 times 5,280. If you have a big screen calculator, you can just put it all in like this with fraction bars, and that works great, but you don't have to have one. So 60 times 5,280 times 12 times 2.54, and that's the last one. That gives me 9,656,060, I think. So now I'm going to divide that by, here I can put in parentheses and then just do 100 times 3,600. Or I could literally just do that answer divided by 100, hit equals, then take that answer and divide it by 3,600 and hit equals. But ultimately I get 26.8224. And that's meters per second. Okay, so meters per second, miles per hour, 60 miles per hour is 26.8224. Now, I only used 1 or 2 sig figs depending on what kind of rule you're trying to use here. But the important point is no matter how many sig figs I put in, I could get that exact same number of sig figs out because all of these were exact unit conversions. There was no round off error in here. The answer is 5,280.0 to an infinite number of places, 12.0 to an infinite number of places, 2.54 to an infinite number of places. So in that sense, it's a lot easier to deal with. So I think y'all can see how we do that. Another one that trips students up is the density calculation. So I like to use the density of water. The density of water is kind of a beast. It is in fact 1,000 kilograms per cubic meter. That's the density of water. Okay. A kilogram is about 2.2 pounds. So 1,000 of those would be 2,200 pounds. That's called a ton, a T-O-N-N-E. Whereas 2,000 pounds, as opposed to 2,200 pounds, 1,000 pounds is what we call a ton, T-O-N, or a short ton. Okay, so a cubic meter of water really weighs a metric ton, T-O-N-N-E, or a metric ton, either way you want to say it, and it's 2,200 pounds. That's a really big deal. So let's convert this first to grams per cubic centimeter. So in doing that, I happen to know that there are 1,000 grams in 1 kilogram. So I'll use that first to correct the math part. So where am I going to put the kilograms, in the top or the bottom?
Bottom.
Very good. So 1 kilogram will go on the bottom, and I'll put 1,000 grams on top. Well, I'll actually put 1,000 instead of 100. Okay, so that's pretty good. But here's the weird part. I think everybody knows, I want grams per cubic centimeter, and I think everybody knows that there's 100 centimeters in 1 meter, just like there's 100 cents in a dollar, right? But here's the problem. That's meters times meters times meters, so I got to do this 3 times. So am I going to put the meter on the top or the bottom in this one? I'm trying to get rid of that meter here, so where do I put the meter on this one?
On the top?
On the top. So I did 1 meter, 100 centimeters, but that just takes care of one of these, and I've got 3 of them, so I got to do it again.
Can you cube the first one?
What's that now?
Can you cube the first one?
Yeah, absolutely. You can either cube it, or I'm just writing it out brute force just one time. But yeah, cubing it would be the exact same thing. So I think you can see I'm going to multiply by 1,000 which would make this 1,000,000, but then I'm going to divide it by 100 times 100 times 100, which is also 1,000,000. So in that case, I now have 1,000,000 divided by 1,000,000, so I get 1 gram per cubic centimeter. So that's the density of water. And that's just a wonderful number to use, right? 1 gram per cubic centimeter. And if you want to talk about salt water, then it's 1.0029. So it's really not that big a difference. Also, you could do it grams per milliliter. Here's the cool thing. A liter is defined to be 10 centimeters by 10 centimeters by 10 centimeters. So I think you can see that 1 liter is equal to 10 times 10 times 10, or 1,000 cubic centimeters. Y'all see that? So what do you think, if a liter is 1,000 cubic centimeters, what do you think 1 milliliter is? How many cubic centimeters?
1.
Exactly. So the conversion factor between a milliliter and a cubic centimeter is just 1. So we can also say this is 1 gram per milliliter. And that's an important thing, especially if you have kids. You often will get doses for your baby or for your cat or dog in milliliters. And like the pharmacist, or excuse me, the doctor will write cc's, and then the pharmacist will write milliliters. You're like, wow, crap, did he screw up? Well, a cubic centimeter is the exact same size as a milliliter. So that's kind of neat, right? So now we've covered unit conversions, and the last thing that we're going to do in this last 15 minutes is I'm going to make use of my fancy cardboard so I don't waste that either. I am going to show you dimensional analysis. So let's start off with some ground rules. Velocity. You all have a speedometer, and we often use speed and velocity interchangeably. In the next couple of chapters, you'll learn they're not interchangeable. But what are the units on your speedometer?
Miles per hour.
Miles per hour. And the mile is a unit of what?
Length and
Distance.
Distance.
Yeah, length or distance, right? And what about the hour?
That's time.
Time.
Time. So in fact, its velocity is equal to distance divided by time. So what that tells us is dimensionally, velocity. So when I put the square brackets around it, I'm saying, hey, let's forget about the numbers and let's just work with the actual dimensions. Now you could also do the same thing and just work with the actual units, but a lot of times we like working with dimensions because that way it doesn't make us use a particular metric system or British system or whatever. So in this case, we're going to say the actual dimensions of velocity are length, which is understood by everybody as L, capital L is length, over time. So I now have that. Acceleration, a lot of people get this one confused. A lot of people don't understand the difference between acceleration and velocity. But does anybody know of any kind of numbers a car dealer or car salesman might give you to tell you how well a car accelerates? There's a bunch of different ones. Let's see if anybody comes up with the one that I'm looking for.
Second 0 to 60.
There you go. That's the beautiful one. Yeah, 0 to 60 is the perfect one. A lot of people will say torque or horsepower, and all those are important. Cubic inches, those are important as well. But really, the actual measurement that is acceleration is 0 to 60. A good car, a fairly good accelerating car, will have a 0 to 60 in 4 seconds. So what you're talking about there is you're saying a change in velocity and given how long it takes. So the units for acceleration, or the dimensions for acceleration, are the same as the units for velocity divided by the units for time, right? We already found out that velocity is L over T, so now I've got L over T divided by T, which is the same thing as L over T squared. By the way, 0 to 60 in 4 seconds is 15 miles per hour per second. And when we start dealing with accelerations, it's probably better to read it not as seconds squared, but something like I just did, 15 miles per hour per second, or 9.8 meters per second, because it tells you, hey, I'm going to change my speed by 9.8 meters per second every second. So when I say the car sped up by 15 miles per hour per second, that's telling you, 0 seconds it's going 0, but at 1 second it should be going roughly 15 miles per hour, 2 seconds 30, 3 seconds 45, 4 seconds 60. That's if it was really a constant acceleration, but cars fairly never do constant acceleration except for like a electric car in which the constant acceleration is 1. Right? So anyways, so there's two fundamental things. Now let's look at another law that equation that you've known. Can anybody tell me one equation you think every human, or at least every American, knows from physics? There's two of them I'm thinking of. Anyone?
F equals MA.
F equals MA. Very good. That's a good one. F equals MA. That was not the one I was expecting, but it is one of the two that I was expecting. I just expected the other one first. So F equals MA is really the one I wanted. The other one, anybody want to take a poke at it? You see it on cartoons, all sorts of places.
E equals MC squared.
There you go. That's the other one. So yeah, that's a couple of helpful ones. F equals MA is what I'm going for, though. So what that tells you is the dimension of force is equal to the dimension of mass times the dimension of acceleration. Well, the dimension of mass is just m. That's one of our base units, right? So it's m, and the dimension of acceleration is length per time squared. So it's length over time squared. So that is the actual dimensions of force. So now, let me show you some cool stuff. With dimensional analysis, I think we can come up with an equation for the velocity of a wave on a string. So V for a wave on a string. Okay, first off, if any of you ever seen a violin, a guitar, any stringed instrument before? Have any of you not seen a stringed instrument before? Let's put it that way. I think everybody's seen a stringed instrument. Do you notice anything different? For instance, if you're looking at a guitar, one string versus the other, what are they? How do they look different?
Thickness and
Thickness, right? So they're all basically the same length. You know, that's got a fretboard, and at the end of that, it's got this little nub where it stops the string, and then the other side's got another little nub thing called the bridge, and that sort of stops the wave as well. So all the lengths are about the same, but the thicknesses are different. So that tells you that the velocity probably depends on, because velocity is equal to frequency times wavelength, and frequency is the music that you're hearing. It depends on some quantity we call mu, which dimensionally is mass per unit length. So that's one of the things I think that the velocity should depend on. Does that make sense to you guys? Like velocity equals frequency times wavelength. The wavelength is basically going to be twice as long as the string, so that's fixed by the two nubs basically. The frequency is what you hear. So that high pitch one would be a high frequency, and that low pitch one would be a low frequency. But in all cases, the frequency times the wavelength has to give you the wave speed. So I've got that the velocity depends on. The other thing is, what do you do to tune your instrument? Do you just change the strings, or is there something mechanical you can do?
You tighten or loosen the strings.
Exactly. So that means it also depends on the tension, which we call strangely T, which is the same thing we use for time, but it's not time, it's tension. So I would suspect the velocity of the wave on a string depends on the tension and the mass per unit length, but the tension is just a force, and we know its dimensions are ml over t squared, right? So let's try something. We know velocity has dimensions of L over T, so I'm going to write the velocity equals mu to the m power times the tension, and I'll put it fancy so it doesn't get confused with the other one, to the n power. Let's just guess. That's just a guess, okay? Now, velocity has dimensions of length per time, which is the same thing as saying length times time to the -1. Remember, flipping a number over changes the exponent to negative. Now that's going to have to be equal to m over L to the lowercase m power times mL over t squared times to the lowercase n power. So let's start working it out. What I have is L to the 1, t to the -1 is equal to, notice there's an m here and an m here. This one's m to the m, this one becomes m to the n. When you multiply numbers with the same base, you do what to their exponents? Y'all remember? Like 2 cubed times 2 squared becomes 2 to what power?
Oh, you add them?
Exactly. So this will be m to the m plus n. Now, similarly, we got L to the m in the bottom, so you could write that as L to the -m, but it's multiplied by L to the n, so you could write it as L to the n over L to the m. Do y'all remember what you do with exponents when it's one over the other? So like, exactly, 2 to the 3rd over 2 to the 1 is 2 to the 3 minus 1. So in this case, I'm going to do L to the n minus m. And then when you raise a power to a power, t squared raised to the n power, what do you do?
Multiply.
Multiply. So the t will be raised to the negative 2n power. So now I've got some equations I can solve. I know that L has to have a power of 1, so n minus m is equal to 1. I know that m isn't present at all here, so I could write that as m to the 0, in which case I'd say m plus n has got to equal 0. And then finally, I know that t has to have a negative 1 power, so I can say negative 2n is equal to negative 1. That's my huckleberry. So I find out that, in fact, n is equal to 1/2. Now I can plug that into here and get that m must be negative 1/2. And then I realize that n 1/2 minus negative 1/2 does in fact equal 1, so that checks. So I think my formula for the velocity of a wave on a string should be, notice the m is the one that's negative, and that's the one I raised the mu to. So the mu is going to be on the bottom, and the n I raised it was the power on the tension, so I'll put t in the top. And then, of course, the fact that it's 1/2 means its exponent is square root. If you look in your book, you will find that is exactly the right equation for the velocity of a wave on a string. And the velocity of a wave on a string is equal to the square root of the tension of the string divided by the mass per unit length. Isn't that cool? So there's one more I'll show you, and that's called the Planck length, lambda sub p. That has units, of course, of length, and it's made up of h bar, which has units of force times meters, basically, times seconds. So force times meters times seconds. So that gives me m and then L squared over, it would have been t squared for force normally, but now since I'm multiplying by seconds, it's going to cancel one of those out. So that's what the units of h are. So these are the things that that this Planck length is going to depend on. It's also going to depend on the gravitational constant of the universe, which has units of force times length squared over mass squared. So G actually has units of m L over t squared times L squared over m squared. So let's work that out a little bit. The units of G would be, this m is going to cancel out one of these down here, so I'm only going to be left with one m on the bottom. I am going to have a t squared on the bottom, and I'm going to have an L squared on top. So those are my dimensions of G. Those are my dimensions of H. And the last thing it will depend on is the speed of light, which is a speed, so it has dimensions of L and T. So let's say lambda P has units of L to the 1. And that's going to be, let's say, H bar to the N times G to the M times C to the L. And let's see if I can get a formula. So I'm going to say L to the 1 is equal to, now H bar becomes M L squared over T to the N power. And actually I should have just put parentheses there. The G becomes L squared over MT squared, and that's to the M power, and the C would be L over T, and that's to the L power. So I've got an M here to the N, I got an M here to the negative M, so it's M to the N minus M. That takes care of the m's, which I will mark out like so. The l's, I have a L to the 2n, a L to the 2m, and a L to the L. So I'm going to say L is equal to 2n plus 2m plus L. And then finally, that after taking care of that T, ooh, this is a negative 2m. Sorry about that. The other one's positive L, and the other one's negative as well. Sorry about that. Ooh, that would have been a bad error. So it's negative 2m plus 2n minus L. And then finally, that gets rid of all our T's. I'm left, or excuse me, all our L's. Stupid me. Now our T's, oh, that's what I did. I switched back and forth. Sorry about that. Let me regroup what I did here. When I did the L, it should have been L to the 2n plus 2m plus 2 plus L. I was right the first time. I got confused with mixing up my L and my T, plus L. And then finally, the T power. The T is going to be negative 2n, negative 2m, and negative L. So negative 2n, negative 2m, and negative L. So I know L gives me 1. So 1 is supposed to be 2n plus 2m plus L. M is supposed to be 0, so n minus m is supposed to be 0. That means n is equal to m. And minus 2m, n minus 2m minus L is supposed to equal, for this is t, that should be 0 as well. So I got n equals m. That can make this to 2 or 4n plus L is equal to 1. And this one can be minus 4m minus L is equal to 0. So if I add these two equations, I get 0. That doesn't help at all.
How long does this class run till, Wes?
Oh God, I forgot. I was thinking it was 10 after. Oh yeah, that's right. Okay, we'll call it a day on that one. I'm sorry, guys. I completely was thinking this was supposed to run till 12:15. I've been, yeah. Sorry, guys. You're free to go. Send me an email with your name before you split. I completely thought it was supposed to end at 12:15, and I even ran over that. We're going to start lab for those of you who have me at lab. So let's take a 10-minute break, and I will send you. I'll send you an email regarding an invitation to the lab. Sorry, folks. Thanks again.
Is it okay? Can you send a picture of these notes? Because it's kind of blurry on Zoom. So, like, I wrote the notes down, but I just want to make sure I got the symbols.
Yeah, you actually see them better on the other video that's already been posted. So I'll also do this. It's normally hard to take a photograph of it. It takes up so much of our memory that I end up basically running out of memory on Canvas. But I'll do this for you, slowly do that. And I'll slowly do this. Also, I'm going to give you, like I said, 10 minutes from now. So let's call this 12:20. So meet back at 12:30 on the other line, the other Zoom meeting. Sorry about that.
Wait, so you want us to email you for attendance this week?
Just chat, not email. Send it through the chat right now. That'll count for your attendance today. Sorry about that, folks. I feel so bad. I forgot the Tuesday and Thursday class goes to 12:15, so I got completely confused. I'll wait for the last person to leave in case anybody has any questions. Thanks for sticking around, even though I was a slacker and ran over time.
You said that these are recorded on YouTube, right?
I've actually put the links in Canvas, and they're going on YouTube. They should be on YouTube tonight.
And I know that someone mentioned it. That it was just like a little blurry on my screen, so it's making it a little hard to see and understand. So is there any way you could focus it next time a little bit better? So it's hard.
Yeah, I don't think it's a problem with focus because I can tell. I'm looking at it in real time. I can tell when the focus goes bad. It's normally a matter of bandwidth issues. So, but I will constantly keep an eye on that, and you should always interrupt me if it starts to go blurry because that'll give me a time to do this right. You know what I'm doing right now. That'll give me time to do that right then when it's most relevant.
Yeah, it was stupid on me. I should probably say it.
No, you're fine. It's cool. You're trying to be polite. It's hard to call that stupid.
Okay, and I have lab with you in 10 minutes, so I'll just see you in a little bit then.
Okay, sounds good.
Bye.
Bye-bye.
And Mr. Younger, I spoke with, I brought it up on Monday about me switching possibly from the Friday lab with the other professor to your Wednesday lab.
Yeah.
Is that still good to go for today? Should I?
Should still be an option. I will email you. What was your name again, David?
David Fletcher.
David Fletcher. Okay, I'll make sure I email you with the list, and I'll let him know that something's come up and you have to switch to the other one. And I'll try to actually get you physically switched. So it's actually official. But until then, we'll have to do it this way. But thanks again, David.
Yeah, no problem. Thank you.
Jacob, do you have a question, or Mimi?
Oh, I have a question about the mastering physics. Is that going to be all our homework from now on?
Yeah, that's where your homework will be. Now, I've only put up chapter 1 and chapter 2 so far, but yeah, that'll be where your homework's going to be. And there's going to be at least 2 assignments every chapter, 1 on concepts and 1 on problems.
Oh, okay. And the last thing I wanted to say was I wanted to apologize for sending the subject line wrong because you didn't know who I was the last time I emailed you.
Okay, gotcha. No problem. Yeah, that's no problem. I remember your email now. Yeah, it's not a big deal. It's just a matter of it makes it hard for me to understand what's being asked, especially if I don't know what class you're in and all that good stuff. In retrospect, I looked at it and I was like, oh, I can figure out she's in 241, but it was too late by then.
Yeah, and for the webcam, I've been trying to search it on Amazon, but all of them cost above $50. Is there one that's like under 15, like you said? Could you possibly send it?
I thought somebody told me they found one on Office Depot or something like that. They're little fisheye cameras, so they're really, really small. But I'm surprised you haven't found it cheaper than 50. I wonder if I misheard someone. The good news is if you're on any kind of assistance, you're now justified in paying for that. The bad news is if I can't find it less than 50, then you're gonna have to suck up $50. But I'll see what I can find for you. Okay. We usually have a system where our school loans out computers with those, or with a webcam, and sometimes they even loan out webcams. But it's my understanding they're currently short. But you could try and see if you can borrow a computer from school with a webcam.
Oh, thank you.
And I'll keep looking for prices for you. Okay.
Thank you. I'll see you in lab.
Okay, see you, Mimi. How about you, Jacob?
I just had a question. I'm going to. Is it working?
Yeah, I can hear you.
Okay, just making sure because I've been having problems in other classes. So for this MyLab thing, I'm going to pick up my textbook like right after this. And everything. I just wanted to know, once I actually register my textbook on the MyLab Mastery, will I be able to just see all the assignments on the tab in Canvas?
Yeah, in that MyLab and Mastering tab, that's where all the homeworks will be. I usually make practice tests and they'll appear on Canvas, but other than that, everything else will be in MyLab and Mastering.
And I don't know if it's like be too much work, but like there's a phone app called Fast Scanner, and you can like take a picture and it basically scans the document.
Does that do a lot less memory and make it like a PDF or something?
No. Yeah, it comes out as you can email it to yourself as a JPEG or a PDF.
Okay, so it would be smaller memory wise.
Yeah.
And what's it called? Fast
Scanner. I put it in the.
Oh, I see it. Yeah, Fast Scanner. Gotcha. That's cool. I know my daughter was using something like that, so I should have asked her. But yeah, I'll do that, and then that way I can still take these photos and put them up for you.
Yeah. Okay.
All right. Thanks, guys.
Just want to check on the homework. All right. See you later.
All right. See ya.